Welcome back. We're talking about stochastic gradient descent, and in particular, I want to look at the problem of variance. This lecture and the next lecture will look at two different ways to reduce it. In this lecture, we're going to be talking about mini-batch. Let's go over the main issue again. The setting that I'm considering here is what we've called in the past stochastic optimization. Specifically, I'm looking at the setting that's motivated by empirical risk minimization problems in learning. F of x is equal to 1 over n times the sum of fi of x. And again, I don't want to compute the full gradient of f because that requires summing the gradient of each fi. For data-driven problems, this means doing a full pass over the data, and this could be very expensive. So SGD, the SGD algorithm is saying that xt plus 1 is equal to xt minus eta times the gradient, not of the full f, but rather of a randomly selected fi, where again, I is a uniform random variable distributed over 1 to n. You can think of that being as your n data points. And the result that we saw last time was that if I run SGD, exactly this algorithm I've written here, then the expected suboptimality is upper bounded by x1 minus x star. This is common, we've seen this everywhere. Our results have to, at some level, depend on how far away we start. Key things we want to look for: what is the dependence on t? Exactly what we saw before, square root of t. What I mean we saw before is exactly what we had in the subgradient case, the deterministic case. And then we had what I wrote as g before, but let me write it out explicitly. This is the variance term. This is the expected value of, in this case, our subgradient, which is this term. So you can think about this as a variance term. And as we've mentioned, this is exactly the problem. As x goes to x star, this term is not going away, whereas it is going away in the deterministic case. Let's go back to that picture we saw at the end of the previous lecture. Let's look at the high variance case. So this is just a simple regression problem. I'm on purpose drawing points that are quite spread out, even though the 45-degree line seems to be the optimal solution. Now, the problem is that stochastic gradient is, in this case, with very high likelihood, going to pick perhaps this point, and then either one of those, it's going to change. Even though you're at the optimal solution, it's going to change quite a bit. We want to think about ways to mitigate this exact problem. A natural way to mitigate it, of course, is to hope for a problem that has less variance. So if we had a setting with the same solution but much more tightly arranged points, then of course we wouldn't have this. Well, what's another way that we can perhaps work a little harder in order to mitigate this problem? A natural idea is, let's think back to our motivation. I don't want to do gradient descent because it's expensive to compute the gradient over all my points. You should think of n as being very large in problems. These are the pertinent problems. Well, SGD is the other extreme. It's saying just pick one point. But of course, we're not restricted to any of those two. Remember that the result that we showed in the previous lecture, our convergence rate for stochastic gradient descent, didn't assume this setting. The only thing that we assumed in order to have this result, the only thing that we need is an upper bound on the variance and the fact that we're using a stochastic gradient. In other words, any algorithm that uses a stochastic gradient, in other words, whose the expectation of that stochastic gradient is in fact an element of the subdifferential, and any algorithm that uses a stochastic gradient whose variance is controlled, like we've written here, enjoy this result that I've written down. Those are the only two properties that we need. So stochastic gradient descent, where we only choose one point at random, as I've as I've written here, that's just one possible version. There's many other ways that we can do this. One very natural idea is to use Minibatch. So Minibatch just says, rather than picking a single point and computing, so when I say a single point, let me just be a little more careful, a single fi, and using the gradient of fi, we instead pick many of these. Some number. What is a number? That's going to be the size of the mini-batch. So let's pick b fi's. fi1, fi2, all the way up to fib, and use the gradient of the average. So in other words, my new algorithm, my mini-batch SGD, is going to look like this. xt plus 1 is going to be equal to xt minus eta. Okay, and what am I going to put in here? Before, I just had the gradient of fi. Now, I'm going to put the sum of the gradient of fij, j equals 1 to b. b is my mini-batch. And I need to divide this by 1 over b. So let's check that this is indeed a subgradient. What do I need to check? I need to check that the expectation of this thing is indeed equal to the gradient at xt. So the expected value of 1 over b times the sum from j equals 1 to b, gradient of fij of xt. Let's be a little more careful. I've been using capital letters to denote random variables. So this is probably what I should do here as well and call this capital I. So I1, I2, up to ij are all uniformly distributed in 1 to n. The same way that before we just had I being uniformly distributed in 1 to n. And we'll talk about this assumption in a second. Let's assume that I choose them independently of each other. That's going to make, actually I guess that's not important. So looking at this expectation, this is equal to 1 over b times the sum from j equals 1 to b of now the expectation of each one of these individually, ij of x, t. Let's look at each one of these. Well, this is the exact same analysis that we did before. So each one of these, its expectation is just the gradient. So this is equal to 1 over b times the sum from j equals 1 to b of the gradient, no more index of summation, of f of xt. And now you can see why I needed to normalize by 1 over b. This is exactly equal to the gradient of f of xt. So this is indeed exactly what we wanted. Does it help? Let's go back to that picture that we saw. This is our high variance regression setting. What happens when we pick just one point, even if we're at the optimal solution? If I just pick one point, basically you can see that no matter what point I choose, it's likely that it's going to ask me to change my solution quite a bit away from the optimal. But if I need to choose 50 points, what is the chance that all 50 points are on one side of the line? You can do that calculation. If we're at the optimal solution and the points are symmetric as I've drawn them, then it's extremely unlikely that you would draw some number of points and that they'd be heavily imbalanced, all telling you to change your line in one direction. So even though they won't be exactly balanced, It would only be exactly balanced if my mini batch was size n, was everything. Still, you can see from this picture that we've significantly reduced the variance. So the advantages of mini batch, I guess I should write, the short answer is it does. It's going to reduce our variance. So what are the advantages and disadvantages of using mini batch? Well, first of all, as we just said, it reduces variance, and this is what we want. The variance is directly in the size of the variance, and upper bound on that is directly features in the bound. So this is good. It reduces the variance. There's a second important factor that doesn't have to do so much with the analysis, but with computational considerations. Mini batch is inherently parallelizable. Because if I have a batch of size B, that means what I'm trying to compute, in our notation, g tilde of x is equal to 1 over b times the sum of gradient of fij of x, and each of these can be computed independently. Each of the gradient terms can be computed independently. In other words, in parallel. So even though gradient descent is an inherently serial algorithm, if we're using larger mini batches, this offers us the opportunity to parallelize. Especially in the context of neural networks, which we haven't discussed too much, these gradient computations are actually very expensive. So this is a great opportunity to exploit parallelism. So these are key advantages. The disadvantages, well, naturally, it requires more work. To compute a gradient with mini batch size b, that's b times more work than computing the gradient of a batch of size 1. On the other hand, parallelism will mitigate that somewhat, but it's still an important thing to consider. More work, namely b times more, per iteration of the algorithm. And there's another disadvantage as well. Well, I wouldn't say a disadvantage, but something that it hasn't delivered to us that we're interested in, and our discussions have been hinting towards. So if we recall from the previous lecture, we finished by pointing out that if we have smoothness and strong convexity, in the setting where we use the full gradient, in the deterministic case, we saw linear convergence. And what linear convergence requires, in addition to strong convexity, is this self-tuning property that smoothness typically gives us, that the gradient goes to 0 as x goes to x star. But even in the mini batch setting, you can see that we fail to have this. We're not going to have, unless b is very large, in other words, unless b is essentially the size of all of the points, which means that my SGD algorithm essentially has reduced to my gradient descent algorithm, then there's still going to be non-zero variance even as x goes to x star. So we still cannot exploit the self-tuning property in the case when f, the overall f, is smooth. And this is important. We need another technique to do this, and this will be the topic of the next lecture. We're going to pick it up then.